This is a lesson on exponential functions. So up till now we've been looking at some of the algebra things, simplifying exponential expressions, dealing with exponential equations, all important stuff because you use them when you're solving questions. But really this unit is about exponential functions. And they represent a specific type of function that we actually looked at in Unit 1 briefly. It was one of the many functions we covered. But here we get to analyze it in a little more detail. So we could start off by recognizing that the form is generally written as y is equal to b to the x. So the idea being that you have a base for an exponential function, so that b represents any real number, and the x will be in the exponent. And there are a couple restrictions that I didn't indicate in the first unit. First off, b has to be positive. Now mathematically you could have a negative base and it works fine, but you lose the capacity to analyze and to do applications with it. So we put the restriction on b is greater than 0, and also we indicate that b cannot be equal to 1, because if you have a base of 1, then you really just have a straight line, and it just doesn't do much for you. So a typical example would be in function notation, f at x is equal to 5 to the x. Y is equal to 1.05 to the x. That's another one. So you have a fractional base. This one has got some transformations built in. Y is equal to 3 times 1/4 to the x plus 1. So we have a vertical stretch factor, and we have a horizontal translation. But the base is just equal to 1/4. Here's another one set up with different variables. D at t is equal to 100 times 0.98 to the t. This is still an exponential function. D, probably depth, as a function of time. So you'll see all these ones. It's very important that you recognize them as exponential functions before you start doing too much with them. So let's sketch a few. Y is equal to 2 to the x, a very basic looking exponential function. So if you key that into your calculator, 2 to the exponent of x, you'd get something like this. You'll probably want to zoom 6 yourself to give yourself a standard window setting. It's not like trig where you're modifying it quite as often. And you'll get a graph looking somewhat like this. Now a few things we need to be aware of with this graph. Probably the first note, the observation I would make, is that the x-axis is a horizontal asymptote, and you can't necessarily tell that from your calculator or from just this graphing software that I'm using, because it looks like it's almost dying right on the axis, but in fact it's going all the way to the left forever. It never touches the x-axis though. It is an asymptote. So that's an important characteristic of exponential functions. And that will, of course, have an effect on both the domain and the range. So the domain is all real numbers. You can plug any number you want into that expression, and you'll get a corresponding y value. X could be negative 200, positive 17. The range, because the x-axis is a horizontal asymptote, the range is always going to be greater than 0. But all real numbers. Now that's true as long as we haven't transformed it. If we start translating the graph up or down, that will change. And the next lesson will cover that in some depth. Another observation, if you take a look at the graph, you'll see that the y-intercept is 1. And that simply means that if you replaced x with 0 into the equation, well, y is equal to 2 to the 0. Well, 2 to the 0 is 1. So we would expect that all untransformed exponential functions will in fact have a y-intercept of 1. So that's something we want to watch for as we get deeper into them. Let's do another one. F at x is equal to 1/3 to the x. So we have a fractional base, but notice the x is still in the exponent. So it's an exponential function. And if you're going to graph this one on your calculator, you probably don't need to be reminded. But close off that bracket, 1 divided by 3 to the exponent of x. And you'll get a graph like this. A few things we want to be aware of with this graph. The y-intercept is still 1. Because it hasn't been transformed at all, it is going to have a y-intercept of 1. But otherwise, this is a decreasing function. So instead of rising, it's going down. And we would expect that with a fractional base. Now I'm going to be a little bit go into more detail shortly on that, but generally you can think of it in those terms. So in general, for y is equal to b to the x, if b is greater than 1, then the function is increasing. So a base of 2, 3, 4. In this case, I've got y is equal to 1.2 to the x. And now that's not a very steep graph, and we're going to analyze that as well. But it's bigger than 1, 1.2 is, and so it is increasing. It's rising as you go from left to right. The other thing is that if b is between 0 and 1, now remember b cannot be equal to 1 nor 0, but if you have a fraction or a decimal between 0 and 1, then the function is going to be decreasing. So for example, y is equal to 1/5 to the x. This is a classic decreasing graph, and if we took a look at the image of it, you could graph this yourself if you wanted, you'll see you get a fairly steep curve, but decreasing like that with the y-intercept of 1. The domain would be all real numbers. The range would still be y greater than 0. So let's consider a couple graphs and do some comparisons. So y1 is equal to 2 to the x, y2 is 10 to the x. So different bases. And this is fairly intuitive. Most people come to this conclusion on their own if they stop to think about it. If you looked at the two graphs, the y2 equal 10 to the x, you could do this on your own or just take my word for it here. You'll see that the 10 to the x is much steeper. And I will formalize this in a few seconds, but as you might guess, the bigger the base, the steeper the graph. If you compared, if you did a quick look at the table of values, you see it makes perfect sense that the bigger the base is going to rise much faster. So as b increases, the graph becomes steeper or gets closer to the y-axis. Now I have to put a little sort of a condition on this. This is only true if b is greater than 1. I know that says if b is greater than 0, but that should be 1. I'm just going to make a quick change to that. So this should be b greater than 1. Because of course b has to be greater than 0. Now we can also look at a couple other ones that give more information on this sort of characteristic. So if you looked at two other ones, and we had y1 is equal to 9 over 10 to the x, so that's the same as having 0.9, and y2 is equal to 1 over 10 to the x. So graphing these both, you can do it on your own, or you can just observe these ones. They both have a y-intercept of 1, but 1 over 10 in red is very steep, 9 over 10 in black is very flat. And this property could be sort of indicated like this. As b approaches 1, the graph approaches y is equal to 1. So in other words, the closer the base is to 1, which 9 over 10 is fairly close, like that's 0.9, the more your curve is going to become like a straight horizontal line. And that's important because some of the applications we look at where you have like a base of 1.02, they really look like they're just straight horizontal lines. So it's not just a case of b getting bigger, producing a steeper one. Really, it's as b gets closer to 1 from either direction, the graph is going to flatten out. So 9 over 10 to the x is a decreasing function, but it's not decreasing at a very rapid rate. It's decreasing at a rate of change of 0.9. So for your information, and that dotted line would represent y equal 1. Now transformations of exponential functions. This is not new, but any sort of function will behave the same. So you do the same rules, even though they're exponential. So if you were to describe the following ones, let's just look at a couple. A simple one would be y is equal to 2 times 3 to the x. Now this is an exponential function with a base of 3. The question is, what do we do with that 2? And the answer is that that's a vertical stretch by a factor of 2 about the x-axis, as always. Now the 3 is the base. It's not a transformation. The only transformation of this curve is that 2. So you would then get a graph looking like this. And what's interesting with this graph is that if you look at it closely, the y-intercept is now 2. And that makes sense because a vertical stretch means that we're multiplying every y-coordinate by whatever factor, in this case 2. So the y-intercept previously was 1. The y-intercept now is going to be 1 times 2 is 2. This one's more complicated. F of x is equal to negative 5 times 1 over 2 to the x plus 1. We in fact have 3 transformations. The negative gives us a reflection in the x-axis. The 5 is a vertical stretch by a factor of 5 about the x-axis. And then the x plus 1 gives us a horizontal translation of 1 unit left. Now, if you were to graph this one, the original graph that I gave is just the untransformed graph. So that's when you haven't done anything. So I'll make a quick note. That's the untransformed. Curve, I'll say. And then the second one is the one we're really looking at. This doesn't give you much information. It's really tough to, make sense of it. If somebody gave me these 2 graphs and I was asked to, well, what has happened to the second one from the first, I'd have a hard time answering it. But make sure on your calculator, this is really what I'm more interested in. If you do graph this one by hand, negative 5, open bracket, you can go times if you want, 1 divided by 2, or go 0.5. But do not forget when you open up your bracket that x plus 1 must be in its own bracket in the exponent. Otherwise, it won't do what it's supposed to do. And that's basically taking care of everything. That's what you're up against with these ones. I'll bring it back. This is really just an introduction to the graphing part of exponential functions. The next lesson will do some sort of problem solving on these, or just questions. And then following that, we'll get into applications. Thank you for